Howdy, Earth Science folks. It's Mr. Bowser here. We're going to talk about the Coriolis effect. Okay, so buckle up because we're really moving right now. All right. We started a set of notes called the break-in wind notes a long time ago, where we did the cause of wind diagram on the top. I'm just going to talk a little bit on the front side of that sheet. We're going to talk about the Coriolis effect portion of the notes, because it's important to understand the Coriolis effect for the next thing we're getting to. So we're going to do a real quick thing on the Coriolis effect. Now, in my classroom, I have all sorts of displays and models I can use to help you visualize Coriolis effect, but I don't have access to that stuff right now, so sorry about that. We're going to have to just stick to the digital resources that we have at our hands here. But let's define it, and then I'm going to show you some examples of it, okay? So, your notes. What am I doing here? What am I doing? I'm presenting. Duh. Okay, that's good. All right. Gotcha. All right, here we go. Hopefully you're recording all this. All right, so here are the notes. All right. This is obviously an older set of notes I had to scrounge up, but we did this portion already where we drew this diagram, where the cause of wind, right? We talked about how it's really the cause, cause of all weather. So what I want you guys to do right now is I want you to write in the Coriolis effect definition. And here it is. All right. The Coriolis. Now, definition is this: because the Earth rotates, right? Because the Earth rotates, air gets deflected. It gets changed in its direction. Now, this is a little bit confusing, but you got to think about it for a second, okay? The Earth is a giant rock, and because it's a rock, it's solid. The entire thing, the entire rock, right, has to spin once every single day, right? The entire Earth has to do that because it's solid, all right? But the atmosphere on top of the crust is not solid. It is a fluid, okay, which means it can flow. So it does not have to rotate like the Earth does. So what happens is the Earth rotates underneath the atmosphere. And if you're on the Earth, which we are, right? When we look up at the atmosphere, something moving in the atmosphere, we see that it appears to get deflected, right? In the northern hemisphere, the atmosphere always deflects to the right of the observer in the northern hemisphere. To the right, not to the east, not to the west, to the north, the south. No, it's always to the right. And that's because the Earth is round and because the Earth rotates once a day, right? Literally makes my day, okay? Should make yours too. So watch this little YouTube thing, and I'll put the YouTube link probably in Classroom so you guys can see this more closely. The video is not the best footage, but this gentleman tries to relate a merry-go-round to the Earth. So if we were looking at the Earth would be in the dead center of the merry-go-round. That would be the North Pole. So we're looking straight down on the North Pole.
To an observer above the merry-go-round, the path of the ball appears straight, while to someone sitting on it, the ball appears to curve to the left. This exemplifies the Coriolis force, whereby to an observer on the rotating Earth, the path of an object appears to be deflected, and this is a result of the Earth's rotation.
Okay, so point of the story there, right? The ball was actually going straight. The merry-go-round was rotating underneath it. If you're on the merry-go-round, it appears as though the ball gets deflected. But if you're off of the merry-go-round, you're staring at this event from above, you see that the ball actually goes straight. That's what our atmosphere is doing. So here's another example. This is an example of an airplane launching from the North Pole, trying to fly straight south, someplace into Africa over here, right? as it's flying, the Earth rotates underneath it. As a result, it gets deflected. Notice from the point of view of the motion of the airplane, it's getting deflected to its right. It's our left because of our view of what's happening here. Okay? So, Coriolis, here's what I want you to write if you haven't got it down already. Because the Earth rotates, air gets deflected, gets changed in its direction. For the northern hemisphere, it's always deflected to the right. Southern hemisphere, again, because the Earth is round, right, it gets deflected to the left, the opposite direction. That means tornadoes, hurricanes, they all spin one way in the northern hemisphere, but they spin the opposite direction in the southern hemisphere. All righty, folks. Them there is the Coriolis effect. Thank you for listening. I'm gonna go now. Still waiting to